Hello there, my name's Jenna Tarshis, and welcome to this episode of Jenna's Math Class. This video will focus on a specific question from Chapter 3 of the Calculus and Vectors course, Optimization. The question can be found on page 202, number 15, in the Connect and Apply section. Here it is. The cost of fuel per kilometer for a truck traveling v kilometers per hour is given by the equation C at v equals v over 100 plus 25 over v. A. What speed will result in the lowest fuel cost per kilometer? B. Assume the driver is paid $40 per hour. What speed would result in the lowest cost, including fuel and wages, for a 1,000 kilometer trip? As I said before, this question is from the optimization unit, which centers around determination of optimal values of a function. The big idea surrounding this problem is finding the minimum costs of two different scenarios. In Part A, we are solving for the speed at which the fuel cost is at a minimum, and in Part B, we are solving for the speed at which the fueling and paying the driver is at a minimum. In order to begin, we need to recall some background information. The derivative is an equation representing the rate of change of a function with respect to a specific variable. The critical point is a value at which the slope of the function is 0, and therefore the derivative is also equal to 0. For example, take this quadratic function. The linear function next to it is its derivative, and the critical point is marked by the orange dot. We must also recall some simple derivative rules. First of all, the power rule. This is one of the rules used to algebraically determine the derivative of a polynomial function. Also, the sum/difference rule. This derivative rule simply states that to take the derivative of multiple functions being added or subtracted together, you must individually take the derivative of each. That being said, let's look back at the question. This intro gives you a rational function to model the relationship between the cost of fuel used versus the speed of the driver. To get a better picture, let's take a look at what this looks like on a graph. So this helps us visualize that the faster the driver goes, the lower the cost of the fuel until he reaches a speed of 50 kilometers per hour. At this speed, the driver is saving the most money on fuel. By traveling at a faster speed than 50 kilometers per hour, we begin to see that the cost of fuel now rises. So Part A is simply asking for the local minimum of the function that we just graphed. By just looking at the graph, we can determine the answer is 50 kilometers per hour, but in a few minutes I will show you how to get this answer algebraically using the derivative and its properties. In Part B, we must make a new equation that represents the cost of the trip, including both fuel and wages. Once we have completed that, we will do exactly the same thing as Part A, which is finding the local minimum of the function. So now that we've reread the question, it's time to start solving. Our first focus will be Part A, and these are the steps we are going to follow. Here I have written out the original equation and have put it in a simpler form to differentiate, simply by rewriting each term with a coefficient in front of it. So from the sum and difference rule, we know that to differentiate this equation, we must find the derivative of each individual term. So I'm going to apply the power rule, as shown in the left corner, and take the derivative of each term. I've brought down the exponent and subtracted 1 from the original exponent. After simplifying, here's what the derivative looks like. Now on to step 2. We must set the derivative equal to 0. This crucial step will give us the value of v at the turning point of the function, where the slope is equal to 0 and the cost is at its lowest. After solving for v, we get an answer of 50, which coincides perfectly with the graph. Therefore, the speed that will result in the lowest fuel cost per kilometer is 50 kilometers per hour. Our second focus will be Part B, and these are the steps we are going to follow. First of all, we need to create an equation for the cost of the total trip so that we can differentiate it and find its local minimum like in Part A. So we have an equation for the fuel cost, which is given in the question, but we need an equation for the cost of the driver in terms of V. So let's write out and organize what we know. The question tells us that the driver is paid $40 an hour, and he will also travel 1,000 kilometers. Also recall the relationship between speed, time, and distance. We know that speed is equal to distance over time, and therefore time is equal to distance over speed. Now combine this knowledge. We know that the distance he travels is 1,000 kilometers, therefore his time is equal to 1,000 kilometers divided by his speed, which we will now represent with a V. Since the cost of his trip depends on his time, we can represent his cost as $40 multiplied by the time he spent driving. Now for the total cost equation, which I will write as T at V. We take the fuel cost, which is the original equation, and multiply it by 1,000 kilometers, since that's the distance we're traveling. And then you add the cost of the driver. After simplifying it into a nice form, we must differentiate the equation using the sum/difference rule and the power rule. Now we set the derivative equal to 0 to find the turning point of the function where the minimum cost occurs. Solve for V and you get an answer of approximately 80.6. Therefore, the speed that will result in the lowest cost, including wages and fuel for a 1,000 kilometer trip, is approximately 80.6 kilometers per hour. Congratulations! You just completed an optimization problem from Unit 3 of the Calculus and Vectors course. Remember these optimization skills that you acquired from this question because this type of problem is solved in everyday life. For example, an architect is the person who designs buildings and in many cases supervises their construction. Besides constructing a functional building, architects must also regularly use skills in optimization. They need to optimize their time of completion of the project, maybe maximize square footage of a space at the lowest cost, or find the most material they can use without going over budget. Optimization is a crucial part of all aspects of this profession. Well, that's a wrap for today. I hope you learned something about optimization. See you for the next episode of Math with Jenna.